Alright, so according to my date stamps here, my videos, it's been at least a month and a half since I've recorded anything. I made a lot of changes, uh, changes nonetheless, I should say. Yeah, the before I was working on the screen, kind of stepped away from that for a bit. I went to memory here. I've revised my memory a good bit, and I'll show that here. So this is actually really cool looking. What I did was I put everything into chips, and I don't know if I covered that in my videos or not. I also noticed I don't have my fans screaming in the background, which is really awesome. I figured out a way to get around that so I don't have the fans screaming all the time, and that's really good. So I'm pretty happy with that. Yeah, so this is pretty cool. The design is really awesome. There's basically a word of memory here on each floor. So you're talking 16 bits of memory on each one of these floors. And that means the whole tower here is 16 words of memory. So yeah, 16 times 16, or basically 256. Is that right? I gotta think my math through here. But yeah, basically, you got 16 words of memory. Each word holds 16 bytes, right? So you got, you'd have like 256 bytes of memory in this whole thing, which is really awesome. At the top here, this whole bell tower looking thing. So basically, each one of these has a color, set of colors. And the way I organized everything here so that everything falls into these like kind of cool patterns where the signal passes in from the top, comes down, and one side carries the write lines and the other carries the read addressing lines. So basically everything kind of falls through here, and you could kind of do a cool little like let's do like a drone fly through here. So yeah, that's pretty cool. But yeah, the design, this was all my design, and yeah, it took a long time to get everything just right. All these chips had to be patterned in a way, like you have to do a geometrical pattern where like one side has to be, like say let's see what it is so I can reference it correctly, but basically if like one side is the right, then you have to flip it to the other end on the B pair. So like one of these would be like A1, then that's like B2, and then A3. So it like makes like a diagonal pattern, and then B4. So like you have to flip the ends to make everything work in this geometric pattern so that everything lines up just right. And then yeah, I just connected everything and like did these little holes through the floor. So getting this all worked out took a long time, but this design is really cool. It's very geometric. It's very like compact. I'm probably gonna get rid of some of the. I'll probably just like get rid of some of this extraneous wiring and just have like one set of wiring that carries down the data on each side or something like that. But yeah, basically it's going to all have to come up to here, and then you need another set of like demuxes. These are switches that have to pass down. Notice everything kind of like hops over here so to connect the two ends. So connecting this end to this end, because they're not connected through here, down here anywhere. So like to connect this side to this side, and then vice versa, this side to this side for the writes, I had to like pass, snake the cables over and figure out how to do that in a way that wasn't too crazy. And then I need another tower for like so basically this can do all the local addressing, right? But to get this switch, to get everything switched, to actually turn like the numerical addressing, so say it's like it's a computer, so obviously, right? So to address everything numerically like a computer should do, you have to convert that at some point into the colors. So that's kind of what this is doing. This takes the color signals, but there's some switching that has to happen here. Now the problem is this doesn't really recognize the standard. When I did it all, it doesn't really use a standard whatever, like four switch. It's kind of hard to explain, but you'd have to look at it on the like on the workbench to see like what's internal and how the switching is done. But basically, there's like one part of these would switch the actual logic, and then there's like a check for a read and a write signal. So depending on which it is, it sends, you know, the correct switching down here that selects the pair, you know, selects the wiring on the read or write lines that comes out down here. So basically that selects the correct color, like say cyan, like so okay, say you do whatever, switch whatever, and say you want to read, well then it would come out on the orange, right? And it would say, okay, you switch cyan, right? So whatever signaling control cyan, you know, whatever the switch numerical whatever is in here to switch to cyan, it would come down to here to cyan. And you could just trust me for now because I'm going to show you all that. Basically it would come down here to wherever cyan is, and then boom, you would come out on here and it go, oh, send a read signal. So it would come out on here. This circuit gets it, right? So it says, oh, okay, read out your data, and then it responds, right, with its data on the data path, and it comes out, and then it's going to come out to wherever here. So yeah, it's quite complex, but yeah, that's only at this level so far. So yeah, we're going to have like these have to be rearranged in such a way to make a pattern, right, so they can connect to these sets of lines. So I've got to do the same kind of geometric pattern I was doing before. I've got to finish A4 here, B4. So it's like A1, B2, and they're facing like this. So A3 and then B4 like that. So once I get them all lined up, and then I get the, you know, the external addressing, that's going to have to go to the next chip. This chip will have to go to a higher chip that addresses it. So there will literally be a line that comes to this chip with addressing at the next layer to switch this chip, right? And then to select it, and then that chip has to pass down signals that come through it basically for the lower level addressing to switch to these chips, right? So that passes an address through it, comes down to here, selects, converts it, selects one of, you know, whatever through here by switching these chips, and then gets passed through and selects. So that's quite complex, and that's just 16 words of memory right there. So that's going to be 16 words times 16 essentially will be the layer I'm going to stop at for now, because there's just no real sense to build much more memory than that at this point. So that will give me 16 times 16, or 256 words of memory, which is technically, that's 4096 bytes. So that would give me 4K of memory at that point. Yeah, 16 times 16, I don't know. My brain is broken at this point. It's quite a lot. So yeah. And then I wanted to show, so this was the old memory cell here. I've got several of these, and actually what I did was I already moved one. Let's see if I can find it now. It should have been over here. Sorry, bear with me. Maybe not ready for prime time, but oh, you know what? I had it moved, and then I did something. I think it unmoved it. That kind of sucks, because I kind of wanted to show it here, but yeah, I think it unmoved what I did. Anyways, I can show you. Actually, we can just do a quick clone right now. I'll show you actually how Axiom works, which is really cool. Axiom is really useful because that lets me do a lot of the manipulation here that would take a lot of time otherwise. So this has saved me a lot of time doing this, and it probably would not nearly be as far as I am without it, since it's really makes things like way easier. Let's just say I'm just going to grab this for now. There's no reason to grab the whole thing. Why not? Now, you know what, like we'll grab the, like, say right here. We don't need the part that's not even done yet. We'll just grab the, like, say right here. Okay, and then so we'll clone that, so that will make a clone right there, just like that. And you can see how this this lets me manipulate these towers very quickly. I highly recommend this this mod if Axiom, if you get a chance to download it. It's very cool. So let's go ahead, and I think we got to do, yeah. So we'll move this up by like say 1. Boom, that should be right about there. Yeah, I think that's the top floor. So if those are all even, which they look to be, yeah, that's an extra floor. We don't really need that. And then we'll just pull this, say like right here. So everything's flush. And I think we're pretty good. Kind of hard to tell from that angle, but yeah, okay. So we're going to go ahead and drop that right there, and you're going to get to see how this, okay, and I don't know why that even happens. Sometimes it just like breaks a bunch of cabling or something. I don't know if it actually broke the cabling or what happened there, but sometimes Axiom doesn't play well, doesn't play super well with my mod, with, what should I say, Project Red. So unfortunately I have some issues there, some compatibility things, but presuming it didn't mess anything up, which I don't know if it did or not, but it looks good. Anyways, it's not really supposed to be functional. It's just going to be a museum piece kind of here. But so like if we look at this, 3, 4, 5, 6, 7, 8, yeah, so this is exactly 8 words of memory in my old style. We'll call this the V2, as I've been calling it. This would be the V2 memory that I had in my first segment, which I don't even have here. I was even older, the first version, and I was in an older game save. But for now, this is the current V3, right? So let's just put it this way, right? This is like transistor logic here, if you want to consider it like that. And the design was a little bit different, but what I did here, now you'll notice is like about half the depth and about the same width as one of these cells, right? So you're talking here, this whole tower of 16 words, right? This was 1 word of memory, right? So this is 1 word right here, this whole thing. And this is 8 words. So basically you need to double this whole structure right here to back to here just to get 1 of these towers. That's about half the width of this. So you're talking what? You're talking a 8, 16, you're talking a 32-fold improvement at least right there alone, maybe more. And yeah, we basically, what we did was we put 4 bits into each one of these chips. So each one of these chips will respond with 4 bits when it's read from. And the read and write is encoded with the same color line. What I was doing before was kind of goofy, like each of these floors was a different color, and it just kind of didn't really make sense when you think about it. It's like, so yeah, when I really kind of did this over, I really worked out a lot of the issues that I had doing this structure, and I made it way smaller, way better, and now it's compacted. So yeah, this is at least, this has been, you know, like I said, this is V2. I don't know, for those of you who want to see, I think it's in an older video now, but I have my V1, which was even bigger than this. So this footprint has really compacted over time. So yeah, we've gotten a lot better in the past, say, couple of years, I'd say. But yeah, this structure is going to be really cool. When it's done, it's going to be really awesome to see. I don't really have too much. I can actually show, I don't know if I have it set up now. I might show that in the next video, where you can actually write to this memory. I had it wired up down here, and it's actually not too hard to select it. We could really do one right now. Let me just see if we can. Why not? Because we can write and read. Realistically, you just need a. Let's go find it here. Some pad. Some like data entry pads here. We can go ahead and say, you know, pop one of those onto the right, pop one onto the read here, and that will let us, you know, read and write data. And then we need the same for say like right here, whoops, we connect it to our, with these it's kind of tricky because you got to rotate them in such a way they don't like to behave too well with the, of course not. Let's do this where we can get we can work with this a little easier if we go to our wires here and say grab a white bundle cable. Sorry, I was not really thinking about doing this in the video, but it makes sense. I'll just show it for what it is, that it actually works and holds some data. So like, let's just say we want to pop some data there onto white, right? We'll go ahead and we'll test it. We'll just put a full gamut on there. For right now, yeah, we'll say write that to the white line right down here. So we say boom, write that to white, and yellow is the right. So that should now have white on, sorry, all data on it. Now what we do is we turn this off to show that in fact there's no data on the bus, right? And then that turns off all those colors there. And then when we want to read it, we go and we say, okay, we want to read out white. And that tells us that white has, in fact, been written to, contains all FFFF. I used bulbs because I was testing. I was trying to get something figured out. There were some bugs, and I had to use individual bulbs to do that. So when I go ahead and I turn the read off, now the lights turn off. Let's go ahead and send it, just say, let's just say we want to do just F, like let's just say the first set, right? And we want to write that to orange, right? So we'll write it to orange now. I don't know what's going on there. Something bugged, I guess. All of a sudden it just wanted to stop behaving. There we go. Now, when I want to go ahead and read orange out, right, I go ahead and put orange onto it, and there's orange. So that tells you that F is, let's say I only wrote that first row. Let's go ahead and uncheck that. So what this will tell you is, in fact, there is no data on there, and it's being read out, so you can see it's there. If I turn off the read for orange, nothing comes out. Likewise, if I turn on the read for white, we get everything, because that's I wrote FFFF. And if I go ahead and, whoops, let's not do that. It's just a read anyway. So let's go ahead and say orange again, and we get just that. So you can see that they can actually contain different things. And then let's go ahead and just put, like, say the last two. So that should be this and this, sorry, that and that onto, say, magenta, right? So we want to encode onto magenta. We go and say write the last two rows onto magenta. So we go ahead and select magenta, and then we uncheck these. And when we select magenta here, now we'll have, well, what did I select? Yeah, I think I selected the, I must have selected like these, I don't know. Let's see. Yeah, but anyways, yeah, so you see how that's got, oh yeah, that's the last two rows. So yeah, because the first row's there. Okay, so that's the last two. So boom, boom, yep, black. So yeah, it's pretty cool. And then likewise, if I want to go ahead and erase, let's just say I want to go ahead and erase magenta. Now I encode nothing onto magenta, and sorry, this is kind of have to be just right here. Boom. Now we go and we read magenta, and there'll be nothing on it. So yeah, and likewise when we go and we read one of the other ones, yeah, I had that on orange, and then white had everything, so let's go ahead and read white, and there's everything. So yeah, that's one one of the memory towers. I had set up before. I had these hooked up to one of these. This is where I had problems, and I was not seeing what I was wanting to see there. So I had to basically create my own little debugging station there and test it out again. And come to find out, I had some errant things going on in the chips, so I fixed that. And yeah. So that's where we're at right now. That's how it compares to the V2 of the memory. It's been a lot of changes, and it's been a long time coming. And I've done a few other things. Realistically, like I said, it's really been just kind of playing around a bit with the screen, designing some stuff. Really kind of that's where I'm at right now. But I figured it was time for a video, so that's that's it. And then next we'll be getting this all wired up, realistically getting maybe about 4K worth of memory going, and then the rest of the processor really from there. I'm done with memory at this point, so yeah, it'll be that'll be the next step, is really getting the processor working. This is really how the addressing works here. This is I'll just show this real quick before we end the video, but this is right here. This is kind of like what the multiplexer became. This would be those chips at the top up there. And so this is how basically a demux would switch the logic for everything. So like basically on this end you have like your read and your write. So this would be like I think this would be like the read, and this would be the write. So when you switch these, it's going to switch both at the same time because they're both turned on. I use the white orange for this, the white orange pair. So when you go ahead and select that, notice that they both select based on the white orange pair from this end. So that's pretty cool. And then when we go ahead and say select one of them, you get that one end. If you go ahead and do the other, then you just get that end. And so that's how that's like basically one end is the read and one end is the write. And so that's how that addresses those sets. So you switch whatever in here, and you select whether it's a read or write, and it carries down, goes to its appropriate chip, and on the read or the write, and happens to write it from there. So or read it from there. So yeah, that's how that all works. Pretty cool, huh?